Right now, sitting as still as you can manage, you are moving around the center of the galaxy at something like 230 kilometers a second. You feel nothing, because the journey is so vast that a single lap takes longer than mammals have existed, and motion that slow against a clock that large registers as perfect stillness. The galaxy is not a fixed picture overhead. It is a system in ceaseless motion, and you are being carried inside it. By the end of this video, you will understand everything that is moving in the Milky Way, and how we measured motion we cannot feel from a seat that never stops, and why the sky's apparent stillness is only the slowness of a far larger clock. Begin with the sensation itself, because it is worth taking seriously before we take it apart. You are, as far as your body can tell, motionless. Nothing presses you sideways. Nothing streams past your face. The room holds its shape around you, and every instinct you have reports that you and the ground beneath you are at rest. That report is not a failure of your senses. It is the honest result of how motion actually works. A body moving smoothly, without speeding up, slowing down, or changing direction, has no way to feel its own movement from the inside, because there is no organ anywhere in the body that detects velocity. What we can feel is change in velocity, a push as a train pulls away, a lurch as a car takes a bend, the drop in a lift. Steady motion produces none of that. A traveler sealed in a cabin gliding at a constant speed has no experiment available, nothing they can drop or swing or pour that would tell them whether they are racing along or standing still. The Earth is exactly such a cabin, and it is a remarkably smooth one. Consider what that cabin is actually doing, beginning with the motion you could almost catch if you watched the sky patiently enough. The Earth is turning on its axis, carrying you eastward as it spins, one full rotation every day. At the latitudes where most people live, that turn is sweeping you along at several hundred kilometers an hour, faster than any train ever built, and at the equator it runs to more than 1,600 kilometers an hour. You do not feel it for the reason already given. It never changes. The same speed, the same direction, hour after hour, for the whole of your life and every life that came before yours. The only evidence your senses are offered is indirect and easy to misread. The sun climbs and sinks, the stars wheel slowly overhead through the night, and it looks for all the world as though the sky is the thing in motion while you hold still. It is the other way round. The turning of the heavens is the spin of your own platform. Read backwards. You are the carousel. The sky only appears to ride. Now lay the second motion over the first. The Earth is not merely spinning in place. It is falling around the sun, held in a closed loop by gravity, and it travels along that loop at roughly 30 kilometers every second. This is a far greater speed than the spin, and it is genuinely difficult to take in. In the few seconds it has taken to read this far, the planet has carried you the better part of 200 kilometers along its orbit, and it has done so without the faintest tremor. A whole world, oceans and mountains and atmosphere and you, is being flung around a star at a speed that would cross a country in minutes, and the tea in your cup does not so much as ripple. Here again, the only sign is indirect, written into the slow march of the constellations across the year, the summer stars giving way to the winter ones as the night side of the Earth is turned to face out along a different stretch of the orbit. The changing seasons of the sky are the second motion made visible, if you are willing to wait months to read it. If you find these reflective explorations of the cosmos meaningful, a like or a subscribe helps us continue making them. And there is a third motion, larger than both, and it is the one this whole story turns on. The sun is not anchored in space. It does not sit at a fixed point while the Earth circles it. The sun, with the Earth and every other planet held in its gravity, is itself in orbit, sweeping around the distant center of the galaxy at that figure named at the outset, something close to 230 kilometers a second. This is the motion you cannot feel and also cannot see, because there is nothing nearby and stationary to measure it against. The whole solar system moves together, you and the sun and the planets all carried along in convoy, and from inside a convoy in which everything travels at once, there is no streaming landscape to mark the passage. It is the cleanest hiding place a motion could have, and yet the speed is real and enormous. In a single second, the sun and everything riding with it shifts 230 kilometers nearer to wherever the orbit is carrying it. And across the minute or two you have spent reading this far, it has moved you something like 15,000 kilometers, more than the full width of the Earth, without a single tremor to give it away. Sit for a moment with the three of them stacked together, because the sum is stranger than any single piece. As you sit in your chair, perfectly still by every measure your body can make. You are turning eastward at hundreds of kilometers an hour, falling around the sun at 30 kilometers a second, and being carried around the galaxy at 230 kilometers a second. Three motions nested one inside another like the wheels of a clock. None of them felt, none of them stopping. The arithmetic of it should be alarming, and instead, it is invisible. The very completeness of the motion is what conceals it. If even one of these movements stuttered, if the Earth's spin hiccuped or the orbit jolted, you would be thrown across the room and would know in an instant that you had been moving all along. It is precisely because nothing ever interrupts the journey that the journey cannot be felt. So why does it all read as stillness when the speeds involved are so enormous? Part of the answer is the smoothness already described, but the deeper part, the part this whole account is built around, is a matter of time. A motion does not announce itself by its speed alone. It announces itself by how quickly it carries you somewhere noticeably different, and that depends entirely on the size of the journey set against the speed of the traveler. 230 kilometers a second is a furious pace by any human standard. Measured against the galaxy, it is a crawl, because the galaxy is so unimaginably large that even at that speed, a single circuit of it takes, not years, not thousands of years, but hundreds of millions of years to complete. The motion is real, and ceaseless, and fast, and the arena is so vast that across a whole human life, it carries you almost nowhere at all. Across an entire human life, that ceaseless 230 kilometers a second moves the sun only a few hundredths of a light year along an orbit that runs tens of thousands of light years around. You travel constantly and arrive nowhere you could ever notice. The center of the galaxy is no nearer at the end of a long life than it was at the beginning. Stillness, here, is not the absence of motion. It is motion measured against a clock so slow that a lifetime cannot register a single tick of it. That is the reframe to carry through everything that follows. The night sky earned its reputation as the very emblem of permanence, the one backdrop that does not change, the fixed thing against which everything else is measured. That reputation is a trick of scale. Nothing up there is fixed. Every star is moving, the sun is moving, the whole disk is turning, and beyond even that the galaxy itself is in motion through the larger crowd of galaxies it belongs to, a fourth movement laid over the three already counted, which we will come to in its place. The sky is not the stillest thing there is. It is one of the most restless, only slowed in our perception by the sheer size of the distances it has to cross before the change becomes visible, which raises the question that the rest of this account exists to answer. If the motion is genuinely there, threaded through everything from the Earth's spin to the turning of the entire galaxy, and if none of it can be felt and almost none of it seen within a single lifetime, then how did anyone ever find it out? How do you measure a movement you cannot sense, from a platform that never holds still, with no fixed ground anywhere to brace a ruler against? The history of that question is the history of how we learned to read the moving galaxy, and it begins with a single, stubborn observation that the so-called fixed stars were not, after all, where the ancients had left them. For as long as people had watched the sky and written down what they saw, the stars had been the one thing that did not move. The planets wandered, which is what their name meant. The sun and moon traveled their own appointed paths. Comets came and went like rumors, but the stars held their places. Night after night, year after year, generation after generation, the patterns returned exactly as they had been left, the same shapes wheeling overhead in the same arrangement, and out of that constancy grew one of the oldest and most reasonable convictions in all of human thought. The stars were fixed. They were the very definition of fixity, the unchanging backdrop against which every moving thing was measured, and the phrase the ancients used for them, the fixed stars, was not a poetic flourish, but a literal description of what anyone could confirm with their own eyes across an entire lifetime of looking. The conviction was reasonable because it was, for the span of any single observer, almost perfectly true. The motion threaded through the stars is real, but it is the slow kind described already, motion measured against a clock so large that a human life cannot read it. A star may be tearing across the galaxy at tens of kilometers a second, and from a distance of many light years that furious pace shows up as the faintest creep across the sky, a shift so small that no eye, however patient, could catch it in a year, or a decade, or a long human life of watching. The ancients were not wrong about what they saw. They were defeated by the brevity of their own observing. To catch the stars in the act of moving You would need a span far longer than any one person possesses, a record reaching back not years but centuries, against which the present sky could be compared, and that is precisely what one astronomer realized he had. Edmund Halley, the Englishman whose name is now fixed to a comet, was in 1718 examining the positions of the brightest stars when he did something that nobody had quite thought to do with the old records. He compared them, carefully, against the positions written down by the astronomers of the ancient world, by Hipparchus and by Ptolemy after him, whose great catalogue of the stars had been compiled some 18 centuries before Halley sat down with it. 18 centuries is a long enough lever to move almost anything. If the stars drifted even slightly, a drift far too small to notice from one year to the next, then 1800 years of that imperceptible creep, added up, might at last grow large enough to see. It had. 3 of the brightest stars in the sky, Sirius, Arcturus, and Aldebaran, were no longer where the ancients had recorded them. The discrepancy was not the small, scattered error one might expect from old instruments and copied manuscripts. It was a definite, consistent shift, all in plausible directions, and in the most striking case it amounted to more than half a degree. The width of the full moon laid down twice over, a gap no careless transcription could explain. The stars had moved. Not the sky as a whole turning, which everyone knew about, but these particular stars, sliding individually across the unchanging pattern of their neighbors, each one carrying itself a little distance from where it had sat when Ptolemy wrote its position down. The fixed stars were not fixed. They had merely been moving too slowly for any shorter record to reveal. This is the discovery we now call proper motion, the genuine movement of a star across the sky, sideways to our line of sight, measured as a tiny angle covered each year. The angle is almost absurdly small. Even the most rapidly drifting of the bright stars shifts by only about 2 seconds of arc in a year, and a second of arc is the width of a small coin seen from several kilometers away. At that rate, the fastest of them would need some 8 centuries simply to cross a span of sky equal to the width of the full moon. That is why no single lifetime could ever catch it, and why 18 of those centuries, stacked end to end, finally could. It is one of the great quiet turning points in the history of looking up, and it is worth being clear about exactly what it overturned. Before Halley, the heavens divided cleanly into the moving and the fixed, a handful of restless wanderers against a permanent stellar backdrop. After Halley, that division collapsed. The backdrop itself was in motion. There was no permanent frame anywhere in the sky, no fixed scenery against which the wanderers performed. There were only objects moving at different speeds and different distances, some fast enough and near enough to catch within a lifetime, others so slow and so far that only the accumulated patience of 18 centuries could betray them. The stillness of the stars had been an illusion all along, and the illusion had a cause, the same cause named in the beginning. The motion was always there. It was hidden by the slowness of the clock. There is a clue buried in which stars gave themselves away first, though Halley could not yet read it. The 3 that had moved most were among the very brightest in the sky, and there is a reason a bright star is more likely to show a large proper motion. Brightness, very often, is a sign of nearness, and a nearby star, like a nearby bird or a nearby car, sweeps across the field of view faster than a distant one traveling at the same true speed. A jet crossing the horizon miles away seems to crawl, while a sparrow passing close to your face flashes by. Both may be moving at similar speeds, but proximity magnifies the apparent motion. The stars that drifted most visibly across 18 centuries were, in the main, the ones nearest to us, their motion enlarged by their closeness, while the far more numerous distant stars held their places so steadily that they still served, for all practical purposes, as the fixed frame Halley measured against. The amount a star appears to move thus folds together 2 things at once: how fast it is truly traveling and how close it happens to lie, and untangling those would take later astronomers a great deal of further work. But the headline was already written. Across the whole sky, in plain sight, the stars were moving. It is worth pausing on the modesty of the method, because it sets a pattern that runs through this entire history. Halley did not build a new instrument. He did not discover a new force or propose a new law. He took a measurement made by long-dead astronomers, set it beside a measurement of his own, and let the long stretch of time between them do the work that no single observation could. The motion of the stars was extracted not from any one night's looking, but from the comparison of 2 looks separated by an age, the present sky against the ancient record. This is how almost all of the galaxy's motion would eventually be caught. Not by feeling it, which is impossible, but by laying one careful observation against another, across a baseline long enough for the slow change to surface. Halley's baseline was time, 18 centuries of it, borrowed from the patience of the ancient world. But there is a limit to what proper motion alone can tell, and it is a limit that points directly to the next problem. The shift Halley found is purely sideways, a motion across the face of the sky. It says nothing at all about whether a star is also moving toward us or away from us, along the line of sight, because motion straight at an observer changes a star's position not at all. It only changes, very slightly and quite invisibly to the naked eye, how near the star is. So even after Halley, half of every star's motion remained completely hidden. And there is a deeper difficulty still, one that would trouble the astronomers who came after him. When Halley said that Sirius had moved, he was measuring its position against the other stars, treating them as the fixed frame. But what if the frame itself was moving? What if some part of what looked like the star's own drift was in fact the motion of the platform from which Halley watched, the sun and the Earth, and the whole solar system sliding through space, so that the nearby stars appeared to shift partly because we ourselves were shifting beneath them? Halley had proved the stars move. He had not, and could not yet, separate their motion from our own. To do that, someone would have to find the signature of the sun's own journey, written into the drift of the stars around it, and read, from inside the moving ship, the direction the ship was sailing. Halley had left a genuinely awkward problem behind him. He had shown that the stars move, but he had measured that movement against the other stars, as though they formed a steady frame, and there was no good reason to believe they did. If everything in the sky is in motion, then a measurement of one star against its neighbors captures only the difference between their travels, not the travels themselves. Worse, hidden somewhere inside every one of those measured drifts was the motion of the measuring platform, the sun and its planets carrying the observer along through space. When Halley saw Sirius shift, he could not say how much of the shift belonged to Sirius and how much belonged to us. The question that follows is one of the strangest in all of observation. How do you measure the motion of the very ship you are standing on, when there is no shore anywhere in sight, no fixed dock to watch slide past, nothing in the entire visible world that you can be certain is holding still? The answer turns out to be hidden in plain sight, and it is the same answer anyone discovers who has walked forward through falling snow, or driven down a road through swirling insects, or moved through any field of scattered points. Look ahead, in the direction you are traveling, and the points seem to open outward, spreading apart and streaming past you to either side as you advance into them. Look behind, and they close together, converging toward a single spot in your wake. You do not need to feel your motion or see any landmark to know you are moving and which way. The streaming of the scenery tells you. The point ahead, from which everything appears to flow outward, marks the direction of your travel, and the point behind, toward which everything converges, marks where you have been. The motion of the traveler is written into the apparent motion of the surroundings, for anyone who knows how to read it. The same must be true, if the sun is moving, of the stars. As the solar system advances through the surrounding swarm of stars, the stars in the direction of our travel should appear, very slightly, to spread apart, while the stars behind us should appear to draw together. This drift would be faint almost beyond belief, buried inside each star's own private motion, and visible only as a slight shared tendency across many stars at once, a whisper of common direction underneath the noise. But if it were there, it would betray the sun's own journey, and it would do so using nothing but the proper motions Halley's successors had begun to measure. Someone simply had to look at enough stars at once and ask whether their movements, taken together, leaned. That someone was William Herschel, and by 1783 he was perhaps the most formidable observer alive. Self-taught, a working musician for much of his life, who had come to astronomy late and built his own telescopes better than anyone else could, he had 2 years earlier swept up a new planet, the first found in all of recorded history, and with it, a reputation that opened every door. He turned that same patience now on the question of the sun's motion. The data he had were almost laughably thin by any modern standard. The measured proper motions of a mere handful of stars, just over a dozen, each one uncertain. With so few, a less careful mind would have found nothing but scatter. Herschel found a pattern. The motions of his stars were not random. Taken together, they fanned outward from one region of the sky and converged toward the opposite region, exactly the signature a moving observer should see, and the point they fanned away from lay in the constellation Hercules. To pull a single shared direction out of a dozen separate, uncertain, individually messy, stellar drifts, each star moving partly on its own account, and only partly in answer to the sun's travel, was an act of real nerve, as much as skill. A more timid analyst would have called the handful of numbers too few and too rough to trust, and left the question alone. It was a remarkable thing to have read from a dozen faint drifts. Herschel had determined, from inside the moving solar system, with no external reference of any kind, the direction in which that system was sailing. The point in Hercules he had identified is what astronomers now call the solar apex, the bow of the ship, the direction toward which the sun is carrying us through the local stars. Directly opposite it lies the antepex, the stern, the point we are drawing away from. Herschel had found the heading of a vessel by watching the way the scenery streamed past its windows, and the vessel was the entire solar system, and the windows looked out on the nearest stars. There is something quietly astonishing in being able to point at it. On a clear night in the northern summer, when Hercules rides high overhead, you are looking very nearly straight out the bow of the ship, toward the precise patch of sky into which the whole solar system, the sun and the earth and you, is steadily traveling. Turn and face the opposite horizon, and you are looking back along the wake, at the stars the sun left behind ages ago, and recedes from a little further every second. The data were crude, and Herschel knew it, and for a while the result was treated with appropriate caution. But it held. As measurements of stellar motions multiplied over the following century and grew vastly more precise, the direction of the solar apex was pinned down again and again, and it sat, then as now, in Hercules, close to where Herschel's dozen uncertain stars had pointed. Modern instruments give the sun's speed relative to the local stars as something around 20 kilometers a second, and a definite direction, up toward Hercules and the neighboring constellation of Lyra. A self-taught telescope builder, working with almost no data, had got the direction of the sun's local motion essentially right, and the method he used, reading the bulk drift of many stars to extract the common motion underneath, became a permanent part of how the moving sky is measured. But notice carefully what this speed is, and what it is not, because the distinction is the whole point of where this story is going. 20 kilometers a second is a real motion, and it is the sun's genuine drift, but it is the sun's drift relative only to its immediate neighbors, the local swarm of stars all around it. It is emphatically not the 230 kilometers a second of the great orbital sweep around the galaxy named at the very beginning, and there is a profound reason the larger motion does not appear in Herschel's measurement. The sun is not orbiting the galaxy alone. The entire local neighborhood, all the nearby stars Herschel watched, every one of them, is sweeping around the galactic center alongside the sun, carried in the same vast convoy at very nearly the same enormous speed. Relative to one another, within that shared flow, the local stars and the sun drift only gently, jostling at 20 kilometers a second like passengers shifting in their seats on a fast train. The train's own great speed cannot be seen from inside, because everyone aboard shares it. Herschel had measured the jostling. The motion of the train itself remained completely hidden, exactly as it must, for the same reason it cannot be felt. There was nothing in his entire field of view that did not share it. To catch the great motion, then, you would have to find something to measure against that stands outside the local convoy, or you would have to abandon position altogether and find an entirely different way to read a star's speed. And there was, in fact, a second blindness still to overcome, narrower but just as real. Everything Herschel had done, like everything Halley had done, depended on motion across the sky, the sideways drift of stars against their background. But a star, or the sun, can also move directly toward us, or directly away, straight along the line of sight, and that motion produces no sideways drift whatsoever, no streaming, no fanning, nothing for Herschel's method to catch. A star sailing straight at the eye sits apparently motionless on the sky even as it closes the distance at tremendous speed. Half of all the motion in the heavens was still invisible, not because it was too slow this time, but because it ran in the one direction that the geometry of position could never reveal. Reading that hidden half would require giving up on where the stars are entirely, and learning instead to read how fast they are coming or going from the only thing they send us, the light itself. The hidden half of every star's motion, the part that runs straight toward us or straight away, had defeated every method built on position. because that motion does not move a star on the sky at all. To catch it, astronomers had to stop asking where a star is and start asking what its light is doing. And the clue they needed was one that anyone has heard 1,000 times without thinking of the stars at all. It is the sound of a fast vehicle passing by. A siren, a train horn, a racing engine. As it approaches, the pitch is high. The instant it passes and begins to recede, the pitch drops, sliding down to a lower note, even though the source itself never changed its tone. Everyone has heard it. Few stop to ask why it happens, and the answer is the key to the whole locked half of the sky. Sound travels as waves, regular pressure ripples spreading out through the air, and the pitch you hear depends on how often those ripples arrive at your ear. When the source rushes toward you, each successive ripple is launched from a little nearer than the one before. So the ripples arrive bunched together, crowded, more of them per second, and a crowd of ripples is a higher pitch. When the source races away, each ripple is launched from a little further off, so they arrive stretched apart, fewer per second, and that is a lower pitch. The note has not changed at the source at all. The motion of the source has compressed the waves ahead of it and stretched them behind, and your ear reads that compression and stretching as a change in pitch. This is the effect named for the Austrian physicist Christian Doppler, who set it out in 1842, and his real boldness was the claim that it could not be a property of sound alone. It must happen, he argued, to every kind of wave, including light. Light is also a wave, and for light the equivalent of pitch is color. A wave of light compressed by an approaching source is shifted toward the blue end of the spectrum, toward shorter, more crowded wavelengths. A wave stretched by a receding source is shifted toward the red, toward longer, more spread out wavelengths. A star moving toward us should therefore be very slightly bluer than it truly is, and a star moving away very slightly redder, the color carrying the same message the siren's pitch carries. It was a beautiful idea, and for more than 2 decades it was almost useless, defeated by 2 practical walls. The first was that the shift is minute. The speeds of stars, enormous as they are a tiny fraction of the speed of light, and the color change they produce is far too small for any eye to notice. No star looks visibly bluer or redder for its motion. The second wall was worse. Even if you could measure a star's color with perfect precision, you would have nothing to compare it against, because you do not know what color the star would be if it were standing still. Without a known starting point, a shift cannot be measured. You cannot say a thing has moved from its mark if you never knew where the mark was. What broke both walls at once was the discovery that starlight is not a smooth wash of color, but a finely ruled code. When the light of the sun is spread into a spectrum, it is crossed by hundreds of narrow dark lines, gaps where particular precise wavelengths are missing, first carefully charted by Joseph von Fraunhofer early in the 19th century. For decades, no one knew what they were. Then, in 1859, Gustav Kirchhoff and Robert Bunsen showed that each chemical element, heated in the laboratory, emits and absorbs light at its own exact and unchanging set of wavelengths, a pattern of lines as specific as a fingerprint. The dark lines in a star's spectrum are the signatures of the elements in its atmosphere. Hydrogen here, calcium there, sodium, iron, each printing its lines at wavelengths that can be measured on a bench to extraordinary precision and that never, ever vary. And there at last was the fixed reference the moving sky had never been able to supply. The laboratory wavelength of a hydrogen line is a mark that does not move. If the same line in a star's spectrum sits a little to the red of where the laboratory says it belongs, the star is receding, and the size of the displacement gives the speed. If it sits a little to the blue, the star is approaching. The displacement is exquisitely small. A star moving along the line of sight at 30 kilometers a second, a respectable stellar speed, shifts its lines by only about 1 part in 10,000 of their wavelength, a nudge no eye could ever catch, but one. A good spectroscope can split apart and measure with confidence. The lines are a dock, a fixed shore, carried inside the starlight itself. This was the escape from the trap that had bound Halley and Herschel both. Their measurements were always relative, one star against another, every reference point itself adrift, because there was nothing in the sky known to be at rest. The spectral line broke that bind for motion along the line of sight. It does not matter that every star is moving. The wavelength of hydrogen, as measured in a laboratory on Earth, is a standard fixed outside the sky entirely, and a star's line of sight speed can be read against it absolutely, with no need to assume any other star is standing still. the light brought its own ruler. The man who first used that ruler on a star was William Huggins, a wealthy Englishman who had built a private observatory and equipped it, unusually for the time, to break starlight into its spectrum rather than merely to map positions. In 1868, he turned his spectroscope on Sirius, the brightest star in the night sky, and measured the position of its lines against their known laboratory wavelengths. They were shifted, very slightly, toward the red. Sirius, his measurement said, was moving away from the solar system along the line of sight at a speed of some tens of kilometers a second. The figure was rough by modern standards, and later much refined, but the achievement was absolute and permanent. For the first time in history, someone had measured how fast a star was moving toward or away, the precise component of motion that no amount of watching its position could ever reveal. The hidden half of the sky's motion had been caught, and it had been caught not in where the star was, but in the color of its light. With that, the toolkit was complete in principle. Proper motion, the slow sideways drift Halley and Herschel had learned to read, gave a star's motion across the sky. The Doppler shift in its spectral lines now gave its motion toward or away. Combine the two and fold in the star's distance, and you have the full three-dimensional velocity of a star through space, its true speed and its true heading, extracted from a being that simply hangs in the dark and shines. We had learned to clock the motion of objects we can never touch, never reach, and never feel move, by reading the angle they creep across the sky and the color of the light they send. Consider how strange that is. A star may lie so far off that its light set out before the pyramids were built, and yet from the faint message that finally arrives, we can state how fast it is traveling and in what direction, to within a kilometer or two a second, having never gone near it. The galaxy's motion was, for the first time, fully measurable, one star at a time. And that phrase, one star at a time, contains the next discovery in embryo. For as long as the spectroscope was aimed at single bright stars, it told single stories. But the moment astronomers began to gather radial velocities in number, sweeping the spectroscope across the stars, strung along the great band of the Milky Way, and asking not what any one of them was doing, but what all of them were doing together, a pattern surfaced that no individual measurement could show. The approaching and receding were not scattered at random around the sky. They were organized. Stars lying in one direction along the band tended systematically to approach. Stars in another direction tended systematically to recede. The whole field of velocities tilted in a smooth and deliberate way that depended on where along the Milky Way you looked. Something was making the entire disk of stars move in a coordinated sweep, and reading that coordination would reveal that the galaxy does not turn the way a wheel turns, all of a piece, but in a stranger fashion that took 2 decades and 2 careful minds to decode. The pattern in the velocities was the clue, and like all good clues, it ruled things out before it revealed anything. The stars along the band of the Milky Way were not approaching and receding at random. Their motions tilted in a smooth, orderly way that depended on the direction in which you looked. Some stretches of the band leaning systematically toward us, others away, a pattern that orderly cannot come from chaos. It has to come from organized motion, the whole disk of stars moving together in some coordinated sweep, and the shape of the pattern holds, encoded within it, the precise manner of that sweep. The task was to read the manner from the pattern, and the first step was to ask what kinds of turning were even possible. The first hint that something organized lay underneath the stellar motions had come earlier, and it had been thoroughly baffling. Around the turn of the 20th century, the Dutch astronomer Jacobus Kapteyn, sifting the measured motions of stars in great numbers, found that they were not random in direction at all. The local stars seemed to belong to 2 great streams, 2 opposing currents flowing through one another in nearly opposite directions, as though the neighborhood were threaded by 2 crowds walking past each other. Nobody could say why. It was a real and repeatable feature of the data, and for 2 decades it stood as a genuine mystery, a sign that the stars around us were moving to some hidden order that no one had yet decoded. The resolution, when it came, would show that Kapteyn had been looking at the rotation of the galaxy itself, glimpsed sideways, and not yet recognized for what it was. There are, broadly, 2 ways a great disk can rotate, and they could not be more different. The first is the way a solid wheel turns, or a vinyl record on a turntable, every part locked rigidly to every other. On a spinning record, the outer rim travels faster than the inner groove, because it has further to go in the same time, but the whole thing completes one turn together. A speck near the center and a speck near the edge keep perfect formation, always on the same radius, always lined up. If the galaxy turned like this, the stars near the sun would all hold station with the sun exactly, moving in lockstep, and from our seat among them there would be no systematic pattern of approach and recession at all. The neighbors would simply ride alongside us, unmoving relative to us, like cars matched in speed on a motorway. The very existence of the orderly velocity pattern proves the galaxy does not turn this way. It is not a rigid wheel. The second way a disk can turn is the way the solar system turns, and it follows directly from gravity. Each star is an independent body, held in its orbit by the gravitational pull of all the mass lying closer to the center than it does, and the strength of that pull. And so the speed of the orbit depends on how far out the star sits. Close to the crowded center, where the enclosed mass is great and the distance is short, stars must wheel around quickly to hold their orbits. Far out toward the sparse edge, the orbits are slower and more languid. This is exactly how the planets behave around the sun, the inner ones racing, the outer ones crawling, and a disk of stars obeying the same rule does not turn as a single rigid object. It shears. Every star keeps its own pace, set by its own distance, and stars at different radii slide steadily past one another as they go. This is what astronomers call differential rotation, and it produces a quite specific signature in the sky. From the sun's own moving vantage, differential rotation paints precisely the pattern that had been observed. Stars lying a little closer to the center than the sun orbit a little faster, and so gradually pull ahead of us and away. Stars lying a little further out orbit a little slower, and so fall behind. Depending on the direction along the band in which a star sits, this overtaking and lagging shows up as approach in some directions and recession in others, swinging smoothly around the sky in a double-lobed pattern as the line of sight sweeps through the disk. Picture runners on a great circular track, each in their own lane, the inner lanes set to run faster and the outer lanes slower. A runner in the middle lanes, glancing sideways as they go, would see those just inside steadily drawing ahead and those just outside falling behind, the whole field sliding past in a smooth and predictable way that depends entirely on which direction they look. The sun is that middle runner, and the sliding of its neighbors is the pattern Oort would soon read. The pattern is not noise. It is the shear of the galaxy itself, read from a chair that is being carried along in the shearing. The theory of such a galaxy was worked out in the early 1920s by the Swedish astronomer Bertil Lindblad, who pictured the Milky Way not as one solid body but as a set of nested subsystems, all wheeling about a single distant center at rates that varied with distance from it. It was an elegant idea, and it made a sharp, testable prediction. The velocities of stars around the sky should trace out a particular smooth double wave as the line of sight turned, with a definite mathematical shape that differential rotation, and only differential rotation, would produce. The prediction was waiting to be checked against the data, and the man who checked it was Jan Oort, working at Leiden in the Netherlands in 1927. Oort gathered the motions of distant stars across the sky and asked whether they followed Lindblad's double wave. They did, cleanly, unmistakably. The stars approached and receded around the band in exactly the smooth pattern a differentially rotating disk requires, and from the amplitude of that pattern, Oort could extract real numbers, a pair of quantities still known today as Oort's constants, that measured the local rate of the galaxy's turning and the way that rate changed with distance from the center. This was the confirmation, drawn straight from the moving sky, that the Milky Way rotates, that it rotates differentially rather than rigidly, and that it wheels about a center lying far off in one particular direction, toward the constellation Sagittarius, where the band of the Milky Way shines thickest and brightest. The galaxy had a center, and everything, the sun included, was going around it. And here, at last, the great motion named at the very beginning was not merely asserted, but measured and made sense of. Oort's analysis, refined by every measurement since, places the center of the galaxy some 26,000 light-years from the sun, and gives the speed at which the sun and its neighbors sweep around that center as something close to 230 kilometers a second. There is the number from the opening, earned. The reason it had stayed hidden from Herschel now becomes perfectly clear in hindsight. Herschel's nearby stars nearly all shared the sun's orbital motion, riding the same enormous current around the same distant center, so that current canceled out of his measurements and left only the small local jostling of 20 kilometers a second. Oort caught the great motion precisely by reaching out to stars far enough away that they did not share the sun's current exactly. Stars at meaningfully different distances from the center, moving at meaningfully different orbital speeds, whose disagreement with us finally let the underlying flow be seen. The convoy had been measured at last, not by stepping outside it, which is impossible, but by finding, within the same vast flow, riders moving at subtly different rates and reading the great motion out of their differences. It is worth holding on to how strange a thing the galaxy turns out to be, mechanically. It is not an object in the way a wheel or a coin or a planet is an object, something that holds its shape and turns all of a piece. It is a swarm of hundreds of billions of independent orbits, each star falling freely around the common center on its own schedule, the inner ones lapping the outer ones over and over across cosmic time. If you could paint a straight radial stripe across the disk, a line of stars running from the center out to the rim, and then wait, the stripe would not hold. The inner stars would race ahead, the outer ones would trail, and within a few turns the straight line would be drawn out and wound around into a trailing spiral, and within a few more it would smear away entirely, sheared into nothing by the differential turning. The disk flows. It is less like a solid plate and more like a slow, luminous fluid of stars, every part of it sliding past every other, bound into a single system by gravity, but never for an instant moving as one, all of which leaves one number hanging in the air, the most quietly staggering of them. The sun sweeps around the galactic center at 230 kilometers a second, faster than any human-made object, fast enough in principle to cross the Earth in under a minute, and yet the circle it must travel is so unimaginably vast, tens of thousands of light-years across, that a single complete lap takes a span of time with no relation to anything in human experience. Not years, not lifetimes, not the whole of recorded history, but a stretch so long that to measure the galaxy's turning, you cannot use any clock built to human scale. You need a different unit of time altogether, one whose single tick outlasts mountain ranges, and the sun has been alive long enough to have counted out only a handful of them. The clock the galaxy keeps has a name. One full circuit of the sun around the galactic center, that single enormous lap at 230 kilometers a second around a track tens of thousands of light-years wide, takes something close to 230 million years, and astronomers call it the galactic year, or sometimes the cosmic year. It is the natural unit of time for anything that happens at the scale of the whole galaxy, the way our own year is the natural unit for anything tied to the sun, and it is worth dwelling on, because almost everything strange about the stillness of the sky comes down to the sheer size of this one number. Notice first that the galactic year is not a thing anyone has ever watched. No observer has seen the sun complete a lap, or 1/100th of a lap, or could ever hope to. The figure is not measured by weighting, it is calculated, divided out from the two quantities established earlier, the speed of the sun's orbit and the size of the circle it travels. Knowing how fast and how far around, you can work out how long, just as you could compute the travel time of a car on a vast ring road from its speed and the road's circumference, without ever following it the whole way round. We know the length of the galactic year the way we know the depth of an ocean we have never drained. By inference, cleanly, from measurements that take an evening, about a motion that takes 250 million years. Set the sun's own age against that clock, and the result is humbling in a very precise way. The sun formed about 4.5 billion years ago, out of the collapse of a great cloud of gas and dust, and 4.5 billion years is roughly 20 galactic years. In its entire existence, from its birth to this moment, the sun has carried its family of planets around the galaxy only about 20 times. The Earth, formed alongside it, has made the same 20 laps and no more. The most ancient thing in your experience, the steady sun that has risen every morning of human history without fail, is in galactic terms barely 20 years old, a young adult that has gone around the block 20 times, and the whole of life on Earth, every creature that has ever lived, has lived out its history within those same 20 turns. Consider where the sun stood the last time it was at roughly this stage of its present circuit, 1 galactic year ago. The orbit is not a perfect closed loop, and the galaxy itself has shifted, so the sun does not literally return to the same point, but 1 galactic year into the past lands us about 230 million years ago, and the Earth of that time is almost unrecognizable. There were no flowers yet, no birds, no creature you would call a mammal in any familiar sense. The great extinction that ended the Permian had only recently swept most of life away, and out of the survivors, the very first dinosaurs were just beginning to appear. All the land of the world was fused into a single supercontinent, one connected mass you could in principle have walked across end to end. That was the world as it was when the sun last passed this way. A single turn of the galactic clock contains the entire reign of the dinosaurs, their rise and their long dominance and their sudden end, with room to spare. One tick, one lap. Wind the clock back a second turn, 2 galactic years into the past, some 460 million years ago, and even the dinosaurs lie far in the future. Life has not yet ventured onto the land in any real way. The continents are bare rock and the whole living world is confined to the sea. Each lap of the sun you peel away strips off an entire age of the Earth, and the sun has only about 20 laps in its whole past to peel. Run them all back, 1 galactic year at a time, and 20 turns is enough to return you to the sun's own birth, to a time before there was an Earth at all, only a collapsing cloud that would become one. Now lay human time against the same scale, and it nearly vanishes. The whole span of recorded civilization, from the first cities to this moment, is a few thousand years, which is roughly 1 part in 50,000 of a single galactic year. Our entire species, Homo sapiens, reaching back to its earliest beginnings, has existed for a few 100,000 years, barely 1,000th of 1 lap. Even the whole sweep of time since the dinosaurs vanished and mammals inherited the Earth amounts to less than 1/3 of 1 circuit. Empires, languages, the rise and fall of every culture that has ever existed, the entire accumulated memory of humankind, all of it fits inside a sliver of a single turn so thin that the galaxy, going about its slow business, would never register that it had happened. We do not live through galactic years. We live, all of us, every life and every civilization stacked together, inside one small fraction of a single tick. Compress one whole galactic year down into a single day, and all of recorded human history would flash past in under 2 seconds of it, somewhere in the last breath before midnight. The entire existence of our species, from its first beginnings, would take barely 2 minutes of that day. And the galaxy itself, vast and ancient as it is, has barely begun to wind. The sun, for its part, has perhaps 20 laps still ahead of it, before it swells into a red giant and ends its life as an ordinary star, which means its entire existence, birth to death, will run to only about 40 galactic years, a life of 40 turns. The Milky Way is something like 13 billion years old, which sounds eternal, and yet measured in its own years that is only some 50 or 60 turns. The structure that looks more permanent than anything, the great wheel of stars that has stood unchanged through the whole of human existence, has in the entire history of the universe completed only a few dozen rotations. A spinning top that had turned 50 times would still be near the start of its spin. By the only clock that suits it, the galaxy is not old at all. It is young and slow and has hardly turned. This is the deepest reason the sky looks frozen, and it is the reframe from the beginning brought to its sharpest point. The night sky is not still. It is turning, ceaselessly, at hundreds of kilometers a second, every star upon its own orbit, the whole disk shearing slowly around its distant center. But it turns on a clock whose single tick is 230 million years long, and a human life, even the entire life of the human species, is far too brief to register any motion at all against a clock that slow. We are not watching a still sky. We are watching a single, motionless-looking frame of an exposure so long that the shutter has been open since before there were creatures to look, and will stay open long after. The stillness is real as an appearance and false as a fact, and the gap between the two is measured in galactic years. There is one more thing the clock implies, and it is the thread that leads onward. If the galaxy truly turns the way the disk's shear has just been laid out, each star orbiting under the gravity of the mass inside its path, with the inner stars racing and the outer stars slowing, then the galactic year is not the same length everywhere. Stars near the center complete their laps far faster. Stars out toward the rim should take far longer, dawdling around enormous slow orbits because the gravity reaching them from the matter further in has grown faint with distance. That is a firm prediction, the same prediction that holds for the planets, where distant Neptune crawls while close Mercury sprints. It says, plainly, that the outermost stars of the Milky Way ought to be the slowest things in it, lagging far behind the brisk inner disk. When astronomers at last measured the speeds of stars right out at the faint edge of the galaxy, expecting to watch them dawdle, they found something that should not have been possible, and it broke the orderly clockwork wide open. The prediction was clean, and it followed straight from everything that had come before. A galaxy held together by the gravity of its visible stars should behave in its outer reaches, like a solar system writ large. Out where the stars thin to almost nothing, and the bright bulk of the galaxy lies far inside, the gravity reaching a star has weakened with distance, and so the star should orbit slowly, the way the outer planets crawl while the inner ones race. Plot the orbital speed of stars against their distance from the center, and the line should rise through the crowded inner galaxy and then bend over and fall away toward the edge, the outermost stars dawdling around their enormous slow loops. That was the expectation. Measuring the real speeds, out at the faint rim, where the prediction was sharpest, would be the test. Our own galaxy is an awkward place to run that test, because we sit inside it, and the view outward is crowded and obscured. It is far easier to measure the rotation of another galaxy, seen whole from outside, its disk tilted to our line of sight, so that one edge sweeps toward us and the other sweeps away. The tool was the one already in hand, the Doppler shift in the light. The approaching edge of a spinning disk has its lines nudged toward the blue, the receding edge toward the red, and the size of the shift at each point gives the orbital speed there. Run a spectrograph across the face of a galaxy, from the bright center out to the dim edge, and you can read off how fast the disk is turning at every distance, the whole rotation laid out as a curve. The astronomer who did this most carefully, galaxy after galaxy, through the 1970s, was Vera Rubin, working with the instrument builder Kent Ford, and a spectrograph sensitive enough to catch the faint outer light most observers had not bothered with. She began with the great spiral of Andromeda and went on through dozens more, patiently tracing each one's rotation from the center outward, further out than anyone had reliably measured before, into the dim margins where the prediction said the speeds must finally fall. They did not fall. Out past the bright disk, where there was almost no visible matter left to see and the orbital speed should have been dropping away, the stars went on circling just as fast as the stars far inside. The curve that everyone expected to bend over and decline simply ran flat, on and on, level to the very edge of what could be measured. The rim of every galaxy was keeping pace, as though gripped by far more gravity than the visible matter could possibly provide. To feel how wrong this is, picture a carousel of horses. On any ordinary carousel, the outer horses sweep around faster than the inner ones, but all of them share the rigid frame. A galaxy has no frame, only gravity, and gravity bound to visible mass demands the opposite, that the outermost riders, far from the bright center, should fall behind and dawdle. To find the outer stars instead, galloping just as fast as the inner ones, is to find a carousel with no frame at all whose outermost horses somehow keep stride with the center, held in formation by a grip that nothing visible is supplying. Either the gravity was coming from somewhere unseen, or something was badly wrong with the rules. It is worth pausing on how stubborn this result was, because that is what made it undeniable. One galaxy behaving oddly might be a fluke, a misjudged distance, a trick of the light. But Rubin found the same thing everywhere she looked, spiral after spiral, the flat outer speeds repeating with a monotony that could not be argued away. She had chosen, characteristically, to push her measurements out into the faint outer regions that most observers passed over as too dim to bother with, and to make her claims slowly and carefully, letting case pile upon case until the pattern was beyond dispute. The measurement itself was beyond reproach. Simple Doppler shifts of the kind Huggins had pioneered a century before, read off cleanly across each disk. The galaxies really were rotating that way. The careful work of one observer, building up a verdict from dozens of consistent cases, had turned an anomaly into a fact that the whole of astronomy had to face, and had done it with the oldest tool in the book. The shift of a line of light turned patiently on the places no one else had looked, and the fact has only one straightforward reading. For the outermost stars to move as fast as they do without being flung off into intergalactic space, there must be far more mass holding them than anything that shines. A great deal of matter, several times more than all the stars and gas put together, must be there, gravitating, gripping the fast outer stars, and yet giving off no light of any kind, no glow, no shadow, nothing the eye or the telescope can see directly. It does not sit in the bright disk where the stars are. It extends far beyond the visible galaxy, wrapping the whole luminous wheel in a vast, roughly spherical cloud of unseen mass, a halo reaching out well past the edge of the light. We had been measuring the size of the galaxy by where its light gave out, and the motion of the stars was saying that the galaxy is far larger than that, most of it dark. This is not a verdict about distant galaxies alone. The same flat behavior has since been traced in the Milky Way's own turning, out beyond the orbit of the Sun, where the disk's rotation refuses to slacken the way the visible mass says it should. Our own galaxy, the one carrying you around at this moment, is wrapped in the same vast unseen halo, and the brisk 230 kilometers a second of the Sun's orbit is held by a grip that reaches from matter we cannot see. The dark thing is not somewhere far off. It is here, around us, steering the local motion this whole account began with. This unseen mass is what astronomers came to call dark matter, and within the story we have been telling, it occupies a particular and unusual place. Every other motion in this account was eventually traced to a cause that could itself be seen or understood: gravity from visible mass, the turning of a measurable disk, the pull of a star we can point to. Here, alone, the motion is measured with complete confidence, and the thing causing it has never been caught. We know it is there exactly as Halley knew the stars had moved, by an effect too consistent to deny, and we know it only that way. Its presence is written in the speeds of the outer stars, and nowhere else available to the eye. It is the one genuinely open case in the whole history of the galaxy's motion, an influence weighed precisely by what it does and still unseen in itself. A careful account has to add that not everyone reads the flat curves the same way. Most astronomers conclude that the extra gravity means extra, invisible mass, and the weight of further evidence has carried the great majority to that view. A minority have asked instead whether the fault lies not in missing matter but in our law of gravity itself, whether the rule that works so well across the solar system might behave differently out at the vast, faint scales of a galaxy's edge. That debate is real, and not for this story to settle. What is not in doubt is the motion. The outer stars move too fast for the visible galaxy to hold them, and whichever way the explanation finally falls, it points to something we do not yet fully understand reaching far beyond the lit disk. That something, that great dark halo enclosing the bright galaxy, is not empty of things we can see. Scattered through it, out in the dim outer reaches where the unseen mass dominates, moves a population of objects far older and stranger than the orderly stars of the disk, traveling on paths that obey none of the tidy rules of differential rotation. To follow the motion outward from the spinning disk into that halo is to leave the brisk clockwork behind and meet the galaxy's oldest and slowest movers, diving on long, steep orbits through the whole structure as though the disk were not even there. Out in the great dark halo, far above and below the bright spinning disk, drift some of the oldest objects in the entire galaxy. They are the globular clusters, tight balls of stars, each one a dense swarm of hundreds of thousands or even millions of suns, packed into a roughly spherical knot, glittering and ancient. The Milky Way carries around 150 of them that we know of, and they are not scattered through the disk where the familiar constellations lie. They are arranged in a vast spherical cloud centered on the galaxy itself, hanging out in the halo above and below the plane, surrounding the disk on every side like a swarm of bees about a hive. One of the finest, the great cluster catalogued as M13, hangs in the constellation Hercules, the very patch of sky toward which the sun is sailing, a city of hundreds of thousands of stars, so old it was already ancient before the Earth existed. These clusters are among the most venerable structures in the galaxy, 12 or 13 billion years old, nearly as old as the Milky Way itself, far older than the sun and its tidy circuit. And the crucial thing about them, for a story about motion, is how they move. They do not ride the disk's orderly rotation. They take no part in the brisk, shared sweep that carries the sun and its neighbors around at 230 kilometers a second in a flat, well-behaved circle. The globular clusters and the scattered individual old stars that share the halo with them move instead on long, steep, lopsided orbits, plunging in from the far reaches of the halo toward the galactic center and then climbing back out again, tilted at every conceivable angle to the disk, diving clean through the plane of the galaxy and out the other side, as though the disk were not even there. Where the disk stars circle like horses on a level track, the halo objects fall like comets, on eccentric paths that pay the orderly clockwork no heed at all. To an observer riding the disk, these halo objects show up in a way that once seemed paradoxical, as high-velocity stars, stars that appear to be racing past us far faster than our placid neighbors. For a long time their speed was a puzzle. The resolution is one of the most satisfying turns in this whole account. and it is the relativity of motion seen one more time. The halo stars are not, by and large, moving especially fast in any absolute sense. They look fast because we are the fast ones. The sun and everything around it is sweeping along on the disk at 230 kilometers a second, and the halo stars are not. They hang back on their slow, steep, randomly tilted orbits while the whole disk, and we with it, races past beneath them. What we read as their great speed is mostly our own orbital motion, seen from the frame of objects that do not share it. The high-velocity stars are simply the ones that stepped out of the convoy, and their apparent haste is the convoy's own speed reflected back at us. Picture standing on a fast-moving walkway in an airport and watching the people standing still on the floor beside it. They seem to stream past you at speed, when in truth they are the ones at rest, and you are the one being carried. The halo stars are those standing figures, holding to their slow, ancient paths, and the rush we see in them is the speed of our own moving floor. The same trick that hid the sun's motion from Herschel now reveals it, written backwards into the rush of the stars that decline to keep pace. This division, between the orderly fast-spinning disk and the slow, steep-orbiting halo, turned out to run deep, and it was the German-born astronomer Walter Baade who first drew it sharply. In 1944, observing under the unusually dark wartime skies over a blacked-out Los Angeles, Baade was able to separate the stars of a neighboring galaxy into two distinct populations. One kind, which he called Population 1, were the younger stars of the disk, rich in the heavier elements and moving with the disk's rotation. The other kind, Population 2, were older, poorer in heavy elements, and belonged to the halo and the central swarm, moving on the plunging orbits rather than the circling ones. The distinction was not merely one of position, but of history and of motion together. The disk held the young, orderly, metal-enriched stars going round in step, and the halo held the old, metal-poor stars that had never joined the dance. Why two such different populations, moving in two such different ways, should share one galaxy is a question whose answer is written into the very orbits themselves. In 1962, three astronomers, Olin Egan, Donald Lynden Bell, and Alan Sandage, looked carefully at the old halo stars, at their plunging eccentric paths and their meager content of heavy elements, and read in them a record of how the galaxy was born. The halo stars and globular clusters, they argued, formed very early, while the young galaxy was still a great, roughly spherical cloud of gas, falling inward under its own gravity, collapsing toward what would become the center. Stars that formed during that early infall were born already moving on steep, plunging, randomly oriented orbits, because that is how the gas itself was moving then, before it had settled. As the collapse went on, the gas, unlike the stars, could collide with itself, and those collisions gradually flattened it and set it spinning, until it settled into the thin, rotating disk in which the sun would much later be born. The stars already formed kept the orbits they had been given. They could not be flattened or slowed, because stars passed through one another's neighborhoods without colliding, and so they were left behind in the halo, frozen onto the plunging paths of the galaxy's first days, while everything formed afterward went round neatly in the settled disk. That is what makes the slow swarm so remarkable to watch. A globular cluster diving through the disk is not just an old object, it is a preserved motion, an orbit handed down unaltered from the galaxy's formation more than 12 billion years ago. Two separate fossils agree on the age. The orbits are one record, plunging and unsettled because the gas was plunging and unsettled when these stars were made. Their chemistry is another, just as eloquent. The halo stars are starved of the heavy elements that later generations of stars would forge and scatter, which means they were born early, before that enrichment, in the galaxy's earliest days. The steep orbit and the bare chemistry are two clocks set independently, and they read the same impossibly early hour. The disk forgot its birth long ago, smoothed and resettled into orderly rotation. The halo never did. When you look out at M13 in Hercules, you are looking at a fossil, not in rock, but in motion. A path traced today, exactly as it was traced when the Milky Way was first assembling itself out of infalling gas, before the disk existed, before there was a sun to carry an Earth around in a tidy circle. The oldest motion in the galaxy is also its least changed, because nothing has ever stirred it. The picture has been deepened since Egan and his colleagues drew it, and the deepening matters. Not every halo star was born in place during a single grand collapse. The Milky Way has spent its long life swallowing smaller galaxies that strayed too close, and the stars of those devoured companions were scattered into the halo too, left on plunging orbits of their own, that record not the galaxy's birth, but its meals. So the halo is part nursery and part graveyard, holding both the galaxy's own firstborn stars and the remains of others it consumed, all of them moving on the steep ancient paths that mark anything not bound into the disk. So the galaxy holds two kinds of movement at once, layered through the same space: the brisk, flat, orderly turning of the disk, and the slow, steep, ancient plunging of the halo, the dance and the stragglers, the settled and the never settled. It would be natural to suppose, having drawn that line, that everything within the bright disk at least keeps step, that the orderly rotation is perfectly uniform, and only the halo breaks ranks. It is not so. Even within the disk, even among the well-behaved circling stars, not everything moves together. There are stars out of step with their neighbors, currents within the current, and threads of stars strung out across the sky that do not belong to the smooth flow at all, and tracing them reveals that the orderly disk is itself stitched through with motion that refuses to fall in line. The disk's orderly rotation is real, but it is not the whole truth of the disk, and the closer you look, the more the smooth flow breaks into texture. The bulk of the stars do circle in their lanes, in step with their neighbors, but woven through that bulk motion are stars, and whole families of stars that move to a different beat, threads and currents and stragglers that do not match the march around them. Reading those out-of-step motions has become one of the richest ways to uncover the galaxy's hidden history, because a star that moves differently from its surroundings is almost always a star with a different story, and its velocity is the thread that, pulled, unravels the tale. The most spectacular of these are the stellar streams. When a small galaxy or a globular cluster wanders too close to the Milky Way, the great galaxy's gravity does not swallow it in a single gulp. It pulls it apart slowly, drawing its stars out by the tide into a long, thin ribbon. The stars are not scattered at random. They are strung out along the very orbit the doomed object was traveling, stretched into a glowing contrail that traces the path of the swallowing, sometimes wrapping right around the galaxy in a great arc. The clearest case was found in 1994, when Rodrigo Ibada and his colleagues identified a whole dwarf galaxy, the Sagittarius dwarf, caught in the act of being torn apart on the far side of the galactic center, its stars unspooling into a stream that loops up and over the poles of the Milky Way. Others have been found since, including thin, delicate streams left by disrupted globular clusters, ribbons of stars only a little wide, stretched across vast lengths of sky. When the great sky surveys of the early 21st century mapped the outer galaxy in detail, the halo turned out to be crisscrossed with these arcs and ribbons, a tangle of overlapping trails that one famous map christened a field of streams, the whole region revealed as a graveyard threaded with the glowing wakes of devoured galaxies. There is more to the streams than a record of past meals. Because every star in a ribbon is falling freely along the same orbit, the shape that orbit takes is dictated entirely by the gravity it moves through, and that gravity is dominated, out in the halo, by the unseen mass found in the rotation curves. A stream is therefore a long, delicate probe of the dark halo itself. The way a ribbon bends, and where it thickens or frays, betrays the pull of matter no telescope can see, so that the streams, read as motion, quietly map the invisible thing that shapes their fall. The debris of the galaxy's appetite has become one of the finest instruments we have for weighing what is dark. What makes these streams a story about motion is how they are found, because on the sky they barely stand out at all. A stream's stars are spread thinly over an enormous arc and mixed in among countless unrelated stars in the foreground and background. You cannot see the ribbon by brightness, the way you would see a cloud. What gives a stream away is that all its stars are moving together, sharing very nearly the same velocity, because they all inherited the orbit of the object they came from. Hunt through the sky not for clumps of light, but for groups of stars marching in the same direction at the same speed, and the streams leap out of the confusion, coherent in motion where they are invisible in position. The galaxy's history of devouring its neighbors is written across the halo in these ribbons, legible only to anyone who reads velocity rather than brightness. The disk has its own quieter version of the same phenomenon. The stars around the sun are not a perfectly smooth, randomly mixed crowd. They include moving groups, loose families of stars that drift through the neighborhood together, sharing a common motion because they were born together in a since-dissolved cluster, or were herded into step by the gravitational nudging of the galaxy's spiral arms and central bar. The nearby Hyades stars are one such moving group, a coherent current within the local flow. This is, in fact, what Kapteyn had stumbled into a century ago with his two opposing star streams. The disk is not a uniform fluid, but a fabric shot through with currents, families keeping their own counsel as they orbit, detectable, again, only by their shared motion. The quiet neighborhood the older sleep versions of this subject like to describe, the calm local pocket of stars, is calm only in the sense that nothing in it moves quickly, relative to us. It is in truth a slow churn of overlapping currents, born together families slowly dispersing, streams of older stars drifting past, the whole local pool stirred by the distant turning of the bar and the arms, none of it still, all of it merely slow. Even the sun's own orbit is less tidy than the simple flat circle described so far. As it sweeps around the galaxy, the sun does not stay glued to the central plane of the disk. It bobs gently up and down through that plane, rising a little way above it, sinking back through it to a little way below, and rising again, completing one such vertical bob every 60 or 70 million years, several times in each long lap around the center. At this moment, the sun sits a little above the midplane, perhaps 60 or 70 light-years up, drifting slowly through its cycle. It is one more nested motion to add to the stack from the beginning, a small vertical rhythm threaded inside the great horizontal orbit, and like all the others, it is far too slow and too smooth to feel. Some have wondered whether these regular passages through the crowded disk plane might disturb distant comets, or coincide with episodes in the history of life on Earth, though any such link remains speculative and unproven, and the bobbing is best understood simply as what it plainly is, another layer of unfelt motion in a body that never holds still. And then there are the genuine escapees, the stars that are not merely out of step, but leaving altogether. Most stars are bound to the galaxy for good, but a few move so fast that the Milky Way cannot hold them, and these are moving fast in earnest, not merely seeming to. Some, called runaway stars, were flung from their birth clusters, or kicked loose when a companion star exploded, sent careering across the galaxy at high speed. A rarer and more extreme kind, the hypervelocity stars, travel faster still, fast enough to climb clean out of the galaxy and escape into intergalactic space, never to return. The leading explanation for these is a violent encounter near the galaxy's very center, where a pair of stars, straying too close to the central mass, can be torn apart, one captured and the other slung outward like a stone from a sling, accelerated to thousands of kilometers a second by the most powerful gravitational engine the galaxy possesses. To picture the speed, the sun's stately orbital pace is 230 kilometers a second. These exiles travel many times faster, fast enough that the entire gravity of a galaxy of hundreds of billions of stars cannot reel them back in. These outbound stars are arrows that point back the way they came, and they all point, when their paths are traced backward, to one place. That is the thread that draws everything in this account together. The disk turns, the halo plunges, the streams unspool, the moving groups drift, the sun bobs through the plane. The hypervelocity stars are flung outward at unthinkable speed. Every one of these motions, orderly or wild, settled or escaping, is referred in the end to a single point, the center of the galaxy, around which the whole structure wheels, and from which the fastest stars are hurled. For most of this history, that center was an inference, a place deduced from the pattern of the turning, hidden behind thick clouds of dust that no ordinary telescope could pierce. It is an inference no longer. In recent decades, astronomers have watched individual stars orbit that central point directly, clocked them as they whipped around it at speeds beyond anything else in the galaxy, and from their motion weighed the unseen thing they orbit. The pivot of all this motion has been caught in the act of holding the galaxy together. For all that the center of the galaxy governs every motion in it, no one had ever seen it. The trouble is dust. Between us and the galactic center lie tens of thousands of light-years of the disk, thick with the fine interstellar grains that dim and redden starlight, and toward the center, the dust piles so deep that visible light from there is almost entirely blotted out, dimmed by many factors before it could ever reach a telescope. To the eye and to ordinary cameras, the heart of the Milky Way is simply hidden, a bright region we know must be there but cannot look at. For most of the 20th century, the center remained exactly what it had been since Oort, a place deduced from the turning of everything around it, never directly seen, What pierced the veil was a change of light. Infrared light, with its longer wavelengths, slips through the dust far more easily than visible light does, and by observing the galactic center in the infrared, astronomers could at last see through the obscuring clouds to the stars crowded behind them. That was the first step. The second was sharpness. The stars near the center are jammed so close together on the sky that an ordinary telescope blurs them into a single smear, and to track them individually required adaptive optics, a technique that flexes a telescope's mirror many times a second to cancel out the shimmering of the atmosphere and restore the image to crispness. Trained on the galactic center through the largest telescopes on Earth, the giant instruments at Keck in Hawaii and the very large telescope in Chile, infrared cameras with adaptive optics could finally resolve the innermost region into a swarm of separate stars, near enough to the center to feel its full grip, and sharp enough to be followed one by one. Over the years, the individual frames accumulated into something no generation before could have possessed. A time-lapse film of the galactic center, decades of images played in sequence, in which the innermost stars can be seen with the naked eye to sweep around their orbits. A real motion picture of stars circling the heart of the Milky Way. The slowest motion in the sky to grasp, the turning of the galaxy, had been compressed, at its very center, into a movie a person could watch. Two teams set out to follow them, and they did so for the better part of 30 years. One, in Germany, was led by Reinhard Genzel. The other, in the United States, by Andrea Ghez. Year after year, through the 1990s and into the new century, each team photographed the same tiny patch of crowded sky at the galactic center, measuring the positions of a cluster of stars that orbit there, the stars now known by names beginning with the letter S. And as the years stacked up, those stars did not hold still. They moved, visibly, from year to year, and not slowly. Plotted across the accumulating images, they traced out curving paths, and the paths were orbits, looping around a single common point, a point at which nothing could be seen at all. One star outshone the rest as a witness. Catalogued as S2, it follows a tight, elongated orbit around that invisible center, and it completes a full circuit in only about 16 years. 16 years. After the galactic year of 230 million, after the globular clusters frozen on their billion-year plunges, here at last was an orbit on a human scale, a star whose entire year an astronomer could watch from start to finish within a single career. And the teams did exactly that. They tracked S2 around its whole path, watched it swing in toward the center, round the unseen point at its closest approach, and sail back out again, returning by the early 21st century to where the tracking had begun. An entire orbit of a star around the heart of the galaxy, caught on film, beginning to end. When S2 came round again to its closest approach in 2018, the event was watched live. The largest telescopes on Earth trained for months on a single star as it raced through the tightest, fastest stretch of its path. There is something almost vertiginous in it, an orbit so vast that its star travels a few percent of the speed of light, and yet so brief by the standards of the galaxy that astronomers could gather, point their instruments, and watch the whole turn happen on schedule, predicted years in advance, and arriving exactly as predicted, the way a returning comet does. Gravity had been caught keeping an appointment at the center of the Milky Way. What S2 does at its closest approach is the most astonishing motion in this entire account. As it rounds the center, at its nearest it passes within about 120 times the distance from the Earth to the Sun, a hair's breadth on galactic scales. And there, whipping around the turn, it reaches a speed of nearly 8,000 kilometers a second. That is not a misprint, and it dwarfs everything else we have met. The Sun ambles around the galaxy at 230 kilometers a second. S2, at perihelion, is moving more than 30 times faster, at a few percent of the speed of light itself, the fastest sustained orbital motion of any star known. The innermost heart of the galaxy, far from being a place of central stillness, is where the most violent stellar speeds in the whole system are found, stars flung around their turns at a fraction of light speed by the thing they orbit. S2 is only the brightest of a whole swarm of these inner stars, dozens of them threading tight, fast, steeply tilted orbits in the small volume around the center, the densest and swiftest stellar traffic anywhere in the Milky Way. The point we had pictured as the calm hub of a slowly turning wheel turns out to be the most furious place in the galaxy, a knot of stars racing around a dark mass at speeds nothing else comes near. And that orbit is a set of scales. This is the oldest trick in the book. the one Newton's law and Cavendish's measurement first made possible, and that has run through this entire history. Watch how something orbits, and you can weigh what it orbits. The size of S2's loop, and the time it takes to go around, set into the same law of gravity that governs the planets and the disk. Give the mass at the focus of its orbit directly, and the answer is staggering. To swing a star around so tightly and so fast, the central object must hold about 4 million times the mass of the Sun. 4 million suns worth of matter, and S2's orbit shows it is packed into a region smaller than the orbit of S2 itself, smaller than our own solar system's outer reaches. There is only one thing that much mass can be when crushed into that little space. It is a supermassive black hole, and it sits, dark and silent, at the exact point about which the entire galaxy turns. The stars have weighed it without ever touching it, purely by the way they move around it, and for tracing those orbits and revealing what lies at the center, Genzel and Ghez were awarded a share of the Nobel Prize in 2020. It is worth holding the two ends of this story together, because they are the same method stretched across an extraordinary range. To weigh the disk, Oort read the slow shear of stars on a clock of hundreds of millions of years. To weigh the center, Genzel and Ghez read the furious sprint of S2 on a clock of 16. Both did the identical thing, the thing this whole account has been about. They could not see the mass, so they watched what it did to the motion of what they could see, and read the unseen out of the seen. The galaxy's hidden architecture, from the dark halo to the dark heart, has been mapped entirely by the orbits it commands. Nothing about the center was ever looked at directly. It was caught, like every invisible thing before it, in the act of moving the stars. There is a temptation to call that central black hole the one truly fixed point in the galaxy, the still pivot around which all the restless motion turns, the anchor that holds the whole turning system in place. It is nearly that. It is the gravitational hub, the disk wheels about, the focus of every orbit, the place the hypervelocity stars are flung from, and the streams ultimately answer to. But it is not at rest, and this is the last turn the story has to take. The black hole anchors the galaxy, but it does not anchor it to space, because the galaxy itself, hub and disk and halo and all, the entire 200 billion star structure with its dark central anchor, is moving bodily through the universe, falling toward its neighbors, carried in a motion larger than any we have yet named. Even the pivot is in flight. To see the galaxy move as a whole, you have to step back far enough that the whole thing becomes a single object, the way a city seen from orbit becomes a single point of light. Stop tracking the individual stars within it. Stop following the disk and the halo and the racing inner orbits, and treat the entire Milky Way, all 200 billion stars of it, as one body with one velocity. That body is not at rest either, and the way to measure its motion is the way every motion in this account has been measured, by the light. With the same Doppler tool Huygens first turned on a single star, now turned on the combined glow of an entire galaxy at once. There is a vertigo in the shift of scale. The disk we have spent this whole account taking apart, the 200 billion stars, the plunging halo, the streams, the 4 million sun black hole at the heart of it, all of that collapses, from far enough away, into a single faint smudge of light with a single velocity, one more moving point among others. The galaxy that contains everything is itself merely a thing that moves, and its motion is the fourth and outermost of the nested layers, the one the opening named and then set aside. The first person to do this did it before anyone even knew what the object was. In 1912, at the Lowell Observatory in Arizona, Vesto Slipher pointed his spectrograph at the faint oval smudge in the constellation Andromeda, the thing then called the Andromeda Nebula, and catalogued as M31, and spread its light into a spectrum. That smudge is worth a glance upward, because on a clear, dark night you can see it with your own unaided eyes, a dim, elongated glow about as wide as several full moons laid side by side. It is the most distant object the naked human eye can reach, its light setting out toward you 2.5 million years ago, around the time the first members of our own genus were walking the earth, and it is coming closer. The faint patch you can find on a dark night is a whole galaxy, larger than our own, falling slowly toward us across the gulf. Measuring its motion in 1912 was a feat of sheer endurance. The light of a whole galaxy, though it comes from hundreds of billions of stars, is spread so thinly across that faint oval that gathering enough of it to record a spectrum took Slipher exposures running across many nights. The precious light accumulated grain by grain on his plates over weeks of patient work. He was measuring, though he could not have said so, the motion of an entire other galaxy. The spectral lines were shifted, and they were shifted toward the blue. By the size of the shift, the Andromeda Nebula was approaching the Sun at something like 300 kilometers a second, faster than almost anything whose speed had then been measured. It was a startling result, and it was made stranger by the fact that nobody yet knew what Andromeda was. For at the time, the spiral nebulae like Andromeda were a genuine mystery. Many astronomers took them for clouds of gas within our own Milky Way. The idea that they were separate galaxies, vast islands of stars lying far beyond our own, was disputed and unproven, and would not be settled until Edwin Hubble, in the mid-1920s, measured the distance to Andromeda and placed it firmly outside the Milky Way, a galaxy in its own right more than 2 million light-years away. Slipher, in other words, had measured how fast Andromeda was moving years before anyone knew it was a galaxy at all. He had clocked the velocity of an object whose very nature was still in doubt, reading its motion cleanly out of its light, while its identity remained unknown, which is a pure distillation of everything this method can do. As Slipher went on to measure more of these spiral nebulae, a pattern emerged that pointed toward one of the largest discoveries in the history of science. For most of them, unlike Andromeda, were not approaching, but rushing away. Their light shifted toward the red. The full meaning of that general flight outward is a story belonging to the largest scales of the cosmos, and to another telling. What matters here is that Andromeda is the conspicuous exception. Against the broad tendency of the distant galaxies to recede, Andromeda comes toward us, and the reason it breaks the rule is precisely that it is close and bound to us. The Milky Way and Andromeda are not lonely islands drifting independently. They are the two dominant members of a small, gravitationally bound family of galaxies that astronomers call the Local Group, a cluster of several dozen galaxies, most of them small, held together by their mutual gravity and orbiting a common center of mass. The two great spirals, our own and Andromeda, anchor the group at either end, with a retinue of smaller galaxies attending each. A third, middling spiral, the Triangulum Galaxy, is the only other member of any size. All the rest are dwarfs, dozens of them, faint and small, including the two Magellanic Clouds that hang near the Milky Way and are visible to the naked eye from southern skies, and the scattered dwarf companions that orbit both giants. Some of those dwarfs are the very galaxies met earlier in this account, the ones the Milky Way is in the act of swallowing, their stars unspooling into the streams that thread our halo. The Local Group is not a still tableau, but a slow gravitational dance of dozens of galaxies, the great ones pulling in the small ones being torn and absorbed, all of it bound and turning. Within such a bound group, the members do not spread apart. Gravity governs them, and gravity, as ever, pulls together. The galaxies of the Local Group fall toward one another and swing around one another exactly as stars do within the galaxy, only slower and larger. Andromeda's blue shift, its approach at 300 kilometers a second, is simply the two largest galaxies of the Local Group falling toward each other under the oldest force in this story, the same pull Cavendish weighed in his shed, operating now between whole galaxies. There is a refinement to that number that closes a circle open near the beginning. The 300 kilometers a second Slipher measured is the approach as seen from the Sun, and the Sun, we have learned at length, is itself in motion, sweeping around the Milky Way at 230 kilometers a second in a direction that happens to carry it partly toward Andromeda. Some of the blue shift Slipher saw was therefore not Andromeda's approach at all, but the Sun's own orbital motion mixed into the measurement, the very same contamination that bedeviled Halley when he could not separate a star's motion from our own. Remove the Sun's known motion, account for the platform's drift, and the true approach of the two galaxies themselves comes out smaller, around 110 kilometers a second. The galaxies are genuinely falling together, but more gently than the raw figure suggests, and untangling the real motion from our own required knowing exactly how we ourselves were moving, the knowledge this whole history was assembled to provide. It is a fitting close to the method. To measure how one galaxy falls toward another, you must first subtract the spin of the Earth, the orbit around the Sun, and the great sweep around the galactic center, peeling away one by one every motion this account has uncovered until only the galaxy's own bare velocity remains. And with this, the stack of motions promised at the very beginning is complete. Sitting still in your chair, you are turning with the Earth, falling around the Sun with the Earth, sweeping around the galaxy with the Sun, and now, with the entire galaxy falling through the local group toward Andromeda. 4 motions, nested one inside the next, from the daily spin beneath you to the slow gravitational fall of one galaxy toward another across 2.5 million light-years, and you feel not one of them. The 4th and largest, named but set aside in the opening, is the galaxy itself in flight. The whole structure, every star and stream and the dark heart at its center, drawn steadily toward its great neighbor by gravity. That fall is not aimless, and it is not endless. Andromeda is not merely drifting nearer, it is on a course, and that course has an outcome, and very nearly a date. The approach measured in a blue shift over a century ago is the early reading of an event that has scarcely begun, the slow opening move of a collision between 2 galaxies that will, in time, remake them both. The date is roughly 4.5 billion years from now. That is when the 2 great spirals of the local group, the Milky Way and Andromeda, having fallen toward each other across the intervening gulf for billions of years, will at last meet and begin to merge. It is an almost unimaginable span of time, and yet it is finite, and it is calculable, fixed by the motion measurable tonight in Andromeda's blue-shifted light. There is a quiet poignancy in the figure, because 4.5 billion years is also, very roughly, how long the sun has left before it swells into a red giant and ends its life as the steady star we know. The 2 deepest events in the galaxy's future, the death of our sun and the collision of our galaxy, are scheduled, as near as we can tell, for around the same distant age. The sun will be guttering out just as the sky itself is torn apart and remade. Forecasting the collision required more than the blue shift, and the missing piece was the hardest motion of all to catch. Andromeda's approach along the line of sight tells us it is coming, but whether it will strike head-on or merely swing past depends on its sideways motion, its drift across the sky, and that motion is so achingly small, smeared across 2.5 million light-years, that it lay beyond reach for a century after Slipher. Only in 2012, after painstaking measurements with the Hubble Space Telescope, comparing Andromeda's position across years of images with extraordinary care, could astronomers finally pin down that transverse drift. It proved to be very small, which means Andromeda is coming almost straight at us. This will be no glancing past but a genuine merger, a head-on encounter of 2 galaxies, and the verdict was reached by measuring a sideways creep so slight it had defeated every instrument until then. The same kind of imperceptible motion Halley first wrung out of the fixed stars, now read between galaxies. The word collision conjures wreckage, stars smashing into stars, and this is the point at which the truth is stranger and gentler than the word suggests. When the 2 galaxies meet, almost nothing in them will actually hit anything else, because a galaxy, for all its hundreds of billions of stars, is overwhelmingly empty space. The stars within it are so tiny compared to the distances between them that the proportions defeat intuition. Scale the sun down to a single grain of sand, and the nearest other grain is not centimeters away but kilometers. A galaxy is a handful of sand grains scattered across a whole continent, with hundreds of kilometers of emptiness between neighbors. Drive 2 such continents of scattered sand straight through one another, and not a single grain need touch another grain. So it is with galaxies. The Milky Way and Andromeda will pass through each other like 2 ghosts, their stars interleaving, gliding past at distances so vast that direct collisions between stars will be essentially non-existent. The sun, if it still shone, and the Earth, if it still circled, would almost certainly sail through the whole cataclysm without being struck by anything at all. Even at the crowded hearts of the 2 galaxies, where the stars are packed most densely, the spaces between them so dwarf the stars themselves that a direct hit remains vanishingly unlikely. 2 galaxies can merge completely, their stars passing through one another twice over, and still the number of actual star-on-star collisions may be counted on the fingers of one hand, or be simply 0. What does interact is not the stars, but the gas and the gravity. The great clouds of interstellar gas in the 2 galaxies are spread broadly enough that they do collide, slamming together and compressing, and that compression sets off a burst of new star formation, lighting the merging galaxies with brilliant young stars. And gravity, reaching across the whole of each galaxy, does the real remaking. As the 2 disks pass through and fall back toward each other, their mutual pull draws out long streamers of stars, vast tidal tails and bridges flung across hundreds of thousands of light-years, the orderly disks distorted into arcs and plumes. They will pass through once, swing apart, slow, and fall back together, again and perhaps again, each passage tearing further at the structure, until over hundreds of millions of years, the two spirals lose their shape entirely and settle, finally, into a single combined galaxy. The Triangulum galaxy, the third spiral of the local group, may be caught up in the event as well, drawn into the merging of its larger neighbors. If an eye could watch the whole approach from the Earth with the millions of years sped up into minutes, it would see one of the grandest spectacles imaginable. Andromeda, today, a faint smudge you can barely find on a dark night, would slowly swell, growing brighter and broader century upon century, until it spanned the sky, a vast, luminous spiral hanging over the world, far larger than the moon. Then the two galaxies would begin to pass through each other, the heavens filling with long, glowing arcs of stars torn out by the tides and ablaze with the light of newborn suns kindled in the colliding gas, the most violent and beautiful sky any world has ever stood beneath. All of it unfolding so slowly that any single night within it would look, as our own does, perfectly still. Individual stars are not destroyed in this, but they are relocated, often drastically. The sun, swept up in the gravitational chaos, could be flung far from where it began, hurled out into the sparse outskirts of the merged galaxy, or even cast into one of the long tidal tails streaming into intergalactic space. Its tidy 230-kilometer-a-second circuit would be gone, replaced by some wholly new and disordered path. The star would survive the collision untouched, and yet end up somewhere utterly unlike the orderly disk it had circled for the whole of its earlier life. And here the whole story of motion this account has traced comes to a kind of end, because the thing that is destroyed in the merger is precisely the orderly rotation we spent so long uncovering. The merged galaxy will most likely not be a spiral at all. The flat, turning disks, the tidy differential rotation, the stars circling in their well-behaved lanes, all of it will be scrambled. The stars of both galaxies, flung onto disordered orbits by the violence of the gravitational encounter, will settle into a great rounded swarm, an elliptical galaxy, a featureless ball of stars moving every which way rather than turning as one. Astronomers have given the future merged object the half-joking name Milky Way. In it, the sun's old 230-kilometer-a-second circuit, the galactic year, the whole flat spinning order, would simply be gone, replaced by the slow random milling of stars on every possible orbit. The disk we live in, which has seemed throughout this account the very model of a permanent structure, turns out to be a passing phase, a temporary tidiness between the chaos of the galaxy's birth and the chaos of its merger. No human will witness any of this. By the time it unfolds, the sun will have brightened enough to have ended life on Earth long before, and our species, if it exists in any form, will be something we cannot imagine, somewhere we cannot guess. And yet the collision is not really a future event in the way a sunrise is. It is a present motion. It is happening now, slowly, the two galaxies already falling, the blue shift already there in the light, the outcome already fixed by velocities we can measure on any clear night. We are not waiting for the collision to begin. We are living inside its opening move, in the same way we are living inside one slow tick of the galactic year, the great change already underway and far too slow to see. The blue shift in Andromeda's light tonight is not a prophecy of a collision to come. It is the collision, in its first and slowest phase, being read off as it happens. The event and its forecast are the same measurement. That we can speak of the galaxy's deep future at all, name the date of a collision 4.5 billion years off, and describe the shapeless object it will leave behind, is the final proof of what reading motion makes possible. From velocities measured in the present, we reconstruct the deep past, the galaxy's birth out of infalling gas, and we predict the deep future, its merger and its transformation, in both directions running the motion forward and backward like a film. But to do that with confidence for the galaxy as a whole demanded something the lone measurements of Slipher and Hubble and the patient star trackers could only approach. The motions not of one star, or a dozen, or a few hundred, but of the whole moving sky at once. Every star clocked together, the entire galaxy's motion captured in a single vast measurement. That is exactly what was finally built, and it has turned the reading of the moving galaxy from a labor of single stars into a survey of more than 1 billion. Every measurement in this account, from Halley's 3 drifting stars to the orbit of S2, was a labor of single objects, one or a few at a time by an observer who chose a target and worked at it. The whole history advanced star by star. What changed everything was the decision to stop choosing targets and simply measure the motion of nearly everything at once, to industrialize the reading of the moving sky and turn it loose on the entire galaxy. The instrument that did this is a European spacecraft named Gaia, launched in 2013, and it is the culmination toward which this whole story has been quietly building. Gaia is a space telescope of a particular and beautiful design. It sits far from the Earth, beyond the Moon, at a stable point in space 1.5 million kilometers out where the pull of the Sun and the Earth balance, so that it can hold steady and observe without interruption, and it slowly spins, sweeping its gaze across the whole sky again and again, year after year, recording the precise position of every star bright enough to register. The same patch of sky is revisited dozens of times over the mission, and each visit refines the measurement. Periodically, the accumulated results are released to the world's astronomers in vast catalogs, and each release has been an event that reshaped the science overnight, a sudden gift of the measured positions and motions of more stars than every previous survey in history combined. After more than a decade of patient scanning, Gaia has now completed its long survey of the sky, leaving behind a record that astronomers will be mining for generations. Over its mission, it has measured nearly 2 billion stars, each one observed not once, but many times, as the spacecraft's slow rotation brought it back into view, and from the repetition comes the motion. Watch a star's position drift across years of measurements, and you have its proper motion, the very thing Halley extracted from Sirius, now rung automatically from 1 billion stars at once. Watch the tiny annual wobble in its position as the spacecraft swings around the Sun, and you have the star's distance, by the oldest geometry there is. And Gaia carries a spectrograph as well, splitting the light of the brightest tens of millions of its stars to read their Doppler shifts, their motion along the line of sight, the measurement Huygens first made on a single star in 1868. Position, distance, motion across the sky, motion along the sight line, for over 1 billion stars, the complete account of where each one is and how it moves. The precision is almost impossible to convey. Gaia measures stellar positions to a few millionths of a second of arc, a micro-arcsecond, an angle so absurdly small that it is like standing on Earth and measuring the width of a human hair laid on the surface of the Moon, or watching a coin and detecting that it is turned by the breadth of an atom. The proper motions Halley could only catch by borrowing 18 centuries of waiting, Gaia measures directly, in a few years, because its eye is so fine that even those almost frozen drifts become legible in a short span. The whole reason the sky looks still, that its motions are too slow to see, is overcome not by waiting longer but by measuring more sharply, until the slowness that hid the motion from every previous age is simply resolved away. What Gaia produced, then, is something no earlier astronomer could have dreamed of holding. A map not of where the stars are, but of how the entire galaxy moves. A measured field of velocities spanning more than 1 billion suns. Every tool in this long history is folded into it. Halley's proper motion, Herschel's reading of the sun's own drift, Huggins' Doppler shift, Oort's rotation of the disk. All of them are present at once, automated and multiplied 1 billionfold. The labor of single stars become a single survey of the moving whole. With such a map in hand, one can do what no one could before. Take the measured motions of 1 billion stars and run them forward or backward, like frames of a film, watching the disk turn, the streams wind up, the merger debris settle, the whole galaxy set in motion as a simulation built not from theory, but from real measured velocities. It is the nearest thing there will ever be to standing outside the galaxy and watching it move, assembled from inside, one star at a time, into a working model of the whole. In that field of velocities, structures that had been faint or invisible sprang into sharp relief. The spiral arms and the central bar leave their fingerprints in the way local stars stream and bunch, herding the disk's motions into patterns Gaia could trace. The moving groups met earlier, the Hyades current and its kin, resolved into clean clumps in velocity, families of stars revealed not by where they sit but by their shared march, exactly as the streams are found. Kapteyn's century-old puzzle of 2 opposing star streams dissolved completely, its every component now mapped as part of the local flow. The whole tangled motion of the solar neighborhood, which had taken generations to glimpse, lay open in a single dataset. And when astronomers did exactly that, the supposedly settled galaxy turned out to be anything but. Gaia revealed that the disk is not the placid, evenly turning wheel it had seemed. It is subtly warped at its edges, bent like the brim of a hat, and worse, it is rippling. Among the stars near the sun, Gaia found a delicate spiral pattern hidden in their up and down motions, a sign that the disk is still vibrating, ringing like a struck bell, from some disturbance in the relatively recent past, most likely the close passage of a dwarf galaxy that plowed through and set the whole disk wobbling. The orderly rotation we spent so long establishing is real, but laid over it is a faint quiver, the galaxy still shaking from a blow it took, a tremor that only a measurement of 1 billion motions could ever have detected. Gaia read the deep past out of the velocities too. Scattered through the halo, mixed invisibly among the local stars, it found a whole population moving in a strange, shared, lopsided way, stars that did not belong to the disk's rotation, and did not match the ordinary halo either. Their common motion marked them as the wreckage of a single large galaxy that the Milky Way swallowed some 10 billion years ago, a major collision early in our galaxy's life, its victim long since torn apart and its stars dispersed, but its motion still preserved, a coherent signature of an ancient catastrophe, legible after 10 billion years, purely because the stars still remember how they were moving. The Milky Way, it turns out, was built in part out of such mergers, and Gaia could reconstruct one of the greatest of them from velocity alone, reading a 10 billion-year-old collision in the way a scattered population still moves together. That swallowed galaxy now has a name, Gaia Enceladus, given for the mission that found it, and its stars are all around us, threaded invisibly through the local sky, betrayed only by the distinctive way they move. Some of the stars not far from the sun are immigrants from that devoured galaxy, ancient arrivals from a body that ceased to exist before the Earth formed, recognizable today by nothing except their shared and foreign motion. The same trick that found the stellar streams, found here in the oldest and largest debris of all. This is where the thread that began with 3 drifting stars arrives. Halley asked whether the fixed stars moved, and answered it with 3. Herschel asked which way the sun was sailing, and answered it with 12. Huggins asked how fast a star approached, and answered it with 1. Oort asked how the disk turned, and answered it with hundreds. Each question was the same question at heart. How do the stars move? And each answer reached a little further into the galaxy. And where each of those answers was the work of a single observer at a single instrument, this last one is the work of thousands. A collaboration spread across a continent and a generation, building the spacecraft, running it, and reducing its measurements into the great catalogs, the lone watcher at the eyepiece become an enterprise of nations. Gaia asks the same question still, and answers it with nearly 2 billion. The whole moving galaxy rendered at last as a single measured thing. Its rotation, its ripples, its swallowed galaxies, its drift toward Andromeda, all present together in one vast field of velocities. The motion that no one can feel and almost no one across the ages could see has been mapped, star by star by star, until the map holds more stars than there are seconds in a human lifetime, which leaves only the stepping back. We have followed the motion outward from the chair to the edge of the local group, and inward through 3 centuries of patient measurement, and the moving galaxy now lies open before us, clocked and charted and understood. It remains to ask what all of it amounts to, this universe of ceaseless motion in which nothing is fixed and nothing is still, and why a sky so restless should have spent the whole of human history looking, to every eye that ever turned up toward it, perfectly and reassuringly at rest. The room around you is still. You have read this while sitting, as near to motionless as a person can be, and nothing in your body has reported otherwise. And yet, in the time it has taken, the Earth has carried you thousands of kilometers eastward on its spin, tens of thousands more around the Sun, and the Sun has swept you, and the whole solar system, the better part of 100,000 kilometers, along its great circuit of the galaxy, while the entire Milky Way, you and the Sun, and the 4 million Sun black hole, at its heart and all, has fallen a little nearer to Andromeda. 4 motions, nested one inside the next, every one of them underway at this exact moment, not one of them felt. You have not moved from your chair, and you have traveled an enormous distance through the universe, as you do every minute of every day, as you have done every moment of your life. This was the promise made at the outset, and it has been kept. The stillness you feel is not a lie your senses tell. It is the truthful report of a body riding a journey too vast and too smooth to register. What looked like the most permanent thing there is, the fixed sky, the unchanging stars, the solid backdrop against which all motion is measured, turns out to be the most restless thing we know, every part of it turning, drifting, plunging, falling. The fixed stars were never fixed. They were only moving against a clock so enormous that a single tick takes longer than the dinosaurs reigned. And against a clock like that, no human life, and no human civilization, and very nearly no span of life on Earth, is long enough to see the hands move at all. The stillness of the sky is not the absence of motion, it is the slowness of the clock. The same tea that did not ripple in your cup while the Earth flung it around the sun at 30 kilometers a second, the same neighbors who seem to sit beside us unmoving while we are all swept around the galaxy together, the same band of light overhead that has held its shape through the whole of recorded history. All of it is testimony not to rest but to a motion too smooth and too vast to feel. What has changed across this account is not the motion, which was always there and always will be, but our knowledge of it. And that knowledge was won by a particular and unbroken line of people who refused to take the stillness at face value. Halley, setting the present sky beside an 18th-century-old catalog and finding that 3 stars had moved. Herschel, reading the sun's own heading out of the drift of a dozen faint stars. Huggins, catching a star's approach in the faint reddening of its light. Lindblad and Oort, decoding the great shear of the turning disk and weighing the speed of our own circuit. Rubin, finding the rim of every galaxy held by a grip nothing visible could supply. Bade, and those after him, reading the galaxy's birth in the plunging orbits of its oldest stars. Ibata, catching a whole companion galaxy in the act of being torn apart. Genzel and Gez, clocking a star around the dark heart of the Milky Way at a fraction of the speed of light. Slipher, measuring Andromeda's fall toward us before anyone knew it was a galaxy. And Gaia, the patient work of thousands, mapping the motion of nearly 2 billion stars at once. One question: how do the stars move? Asked over and over for 3 centuries, each answer reaching a little further, until the whole moving galaxy lay open and charted. The motion no one can feel was caught, in the end, by people who were determined to measure what they could not sense. It would be easy to find something cold in all this, to feel that a sky in ceaseless motion is a lonelier thing than a fixed one, that to be swept helplessly through space at hundreds of kilometers a second is less of a comfort than to stand on solid, settled ground beneath unchanging stars. But the history just traced points the other way. The comfort was never really in the stillness, which was only ever an illusion of scale, a trick the size of the galaxy played on the brevity of a life. The comfort, if it is anywhere, is in the comprehension. We are not stranded on a motionless rock beneath a frozen sky. We are riding a vast, intricate, knowable voyage, and against every expectation we have learned to read it, to measure our own speed, and our heading, and the distant shore we are bound for, all from a chair that never once stops moving. A motion understood is not a thing to be uneasy about. It is among the most astonishing feats our species has ever managed, and it turns the plain, quiet night sky from a still ceiling into something far grander, the deck of a moving ship whose entire course we have charted from on board. Hold. At the last, the image the whole of it builds toward. You are a passenger aboard a vessel of 200 billion stars, on a voyage so immense and so perfectly smooth that the journey feels for all the world like rest. The ship makes no sound, gives no lurch, shows no streaming landscape at the window, and so its passengers spent the whole of their history believing themselves becalmed. And then, without ever once stepping off the ship, without any fixed shore to sight against, those passengers worked out the entire voyage from inside the cabin. They read the ship's speed from the way the distant stars stream past. They found its heading by the spreading of the lights ahead. They weighed the dark engine at its center by the swing of the nearest stars around it. They traced, in the wakes threaded through the halo, the smaller vessels this one has overtaken and swallowed. And they sighted, far off across an ocean of 2.5 million light-years, the great shore the ship is bound for, and named the age at which it will arrive. They charted the voyage in both directions too, not only where the ship is headed but where it set out, the cloud of gas it first condensed from, the smaller vessels it has run down and swallowed along the way, the long log of a journey of billions of years, all of it reconstructed from inside a single cabin in a single human lifetime, out of nothing but the way the lights outside the window move. The becalmed feeling was never the truth of the voyage. It was only the smoothness of a passage measured against a clock that turns once in 250 million years. And the passengers, in working all of this out, did something far stranger than feeling the motion would have been. They proved it, in detail, with numbers, from a chair that never stopped moving. If you enjoyed this exploration of the silent motions that carry us through the galaxy, a like or a subscribe helps us continue making them. So the next clear night, when you step outside and the sky stands overhead as fixed and quiet as it has looked to every human being who ever lived, you might hold both things in mind at once. The stillness is real, as a feeling, and it is false, as a fact. The band of the Milky Way arching over you is the edge of a turning disk you are embedded in and carried around. The stars scattered across the dark are each upon their own long path, the nearer ones already creeping, century by century, out of the shapes the ancients drew. The faint smudge in Andromeda is a whole galaxy falling slowly toward your own. And you, standing still with your feet on the ground, are being turned and carried and swept and drawn through space along four motions stacked one inside another, none of which you will ever feel, all of which we have learned to read. The sky was never the still thing it seemed. It was always the voyage, and we have only lately learned to chart it. The universe still has plenty left to reveal, and we will be following it as it does.